Hello everyone, I'm Akinori Inoue, Front-End Engineer. In this session, I will discuss solving the layout shift problem in Line News. I am in my third year as a new graduate at Line, and I am involved in the development of Line News and Line Schedule as a front-end engineer. In this session, I will briefly touch on the Line News service, and in the first half of this session, I will introduce a layout shift problem that Line News is facing. In the second half, how we implemented skeleton screen as a solution for layout shift, what problems we encountered, and how things have changed will be covered. First, let me introduce Line News. As of August 2021, Line News has 77 million monthly active users and 15.4 billion monthly PVs, a service used by a large number of users. Typical functions include the digest, which sends articles to Talk, and the News tab, which is the entrance to Line News as shown on the slide. Some functions such as News tab are realized with WebView. Line News uses WebView or Web Front-End technology, but even with that, the technology stack differs from pages to pages. In this session, we will deal with News tab. The News tab was developed using TypeScript and React, and has a variety of functions such as displaying a list of articles, summaries of weather and stock prices, and more recently, summaries of COVID-19. There are so many APIs and React components to handle. Now, the main point of this session. What problems do you think exist in the front-end development of news services? A recent problem we have had is the layout shift problem, which is the topic of this session. More features are added to News tab day and night, and the number of API calls is increasing day by day. This brought the issues of layout shift to the front end, and we needed to work on solving the problem. Layout shift refers to the shifting of the layout that occurs over a period of time. I'm sure you've all seen the shift of layout in a web page due to the insertion of ads after it has been displayed once. Such layout shift may induce incorrect operation. Layout shift occurs because the time taken for API response and rendering is different for each UI component. And in Line News, there was a factor that caused layout shift due to response and rendering speed. It is a property of the API. Line News has a lot of APIs, and among these, three most unique features are personalization, A/B testing, and advertisements. Personalization is a system that provides contents and layout that matches the interest of each user. Line News in the lineup is the most focused area for us since it can show more different contents and design according to the differences of user properties than the regular web service. From a development point of view, the CDN cache cannot be used because the response content is different for each other. Although it depends on each API, APIs that act on individual users tend to be slower to respond than normal APIs because they require authentication and access to a specific database. Next is about A/B testing. At Line News, we often conduct A/B testing when we release new UI and UX. We prepare multiple UI components and their combinations and use the test figures to determine which option is most effective. In addition, when developing and releasing new features, we conduct rollout to release features in stages in order to minimize the impact on users when problems occur. Finally, let me explain how advertising works. Line News distributes advertisement through Line's proprietary platform. Based behind the scenes of the APIs that retrieve data, sorting by user, inventory management, etc. is done in real time, which makes the response time slower than normal APIs. These 3 APIs take longer to respond than normal APIs and change layout depending on the response results, which cause problems of layout shift. So we decided to introduce a skeleton screen to solve this layout shift problem. A skeleton screen is a way to represent only the framework of the content until the required resources are loaded. In a typical skeleton screen, the image and title portions of the UI components are filled with gray elements, and the height for the content is reserved in advance. Then, when the resources necessary to draw the content are available, the skeleton screen and the contents are switched so that layout will not shift. In order to switch between the skeleton screen and the content without shift, their heights need to be perfectly aligned. This means that you need to know the layout information from the stage when the content resources are not yet ready. Now, the 3 APIs of line use I talked earlier can cause layout shift. But they also significantly change the layout and content heights depending on the response results. For example, in the case of personalization, the order of the components displayed depends on the result of the API response. If it is an A/B testing, you might not draw a particular component at all. In the case of ads, different sizes of ads may be displayed each time, depending on the ad inventory. In other words, it was not possible to implement a general skeleton screen that reserves the height in advance for line use, where the layout and content height changes depending on the API results. So we decided to implement our own skeleton screens. It is a way to cover the entire screen with a single skeleton screen. By doing this, you don't have to take into account the design of each UI component and what layout they are placed in. When you hear this, you may think, if the layout changes a lot depending on the API response, there will be a design gap between the skeleton screen and the actual content, and it will be uncomfortable when the skeleton screen is released. We are also concerned about this before implementation. However, with some ingenuity, we were able to eliminate that concern. The first was to fine-tune the fade-out animation when switching. Another thing we did was to make the skeleton screen design more like a layout that appears more often. Especially the skeleton screen at the top of the screen, where users' eyes tend to focus, has been made as close as possible to the actual content, which I think has eliminated a lot of discomfort when the skeleton screen is released. I'll show you a demo of a skeleton screen actually running on News tab. How was it? I don't think you felt any discomfort. So far, I have introduced the concepts behind our skeleton screen UI, and there is one more important element. That is, under what conditions should the skeleton screen be released? As mentioned earlier, the layout and height of the content is highly dependent on the API response, so let's first consider the release conditions based on the API. For example, how about making it a condition that all APIs you are requesting must complete? This is not a good idea. In line use, there are more than 20 APIs that are called immediately after opening a page. Therefore, if you wait for all APIs, it is very likely that the skeleton screen will be released extremely slowly. Also, the number of APIs is not fixed and may change depending on lazy loading and server response status, so it is ambiguous how far you should wait for an API. So what if the release condition is the completion of a specific predetermined API? This is also difficult because the API to be called changes for each other depending on the personalization mechanism. In the first place, if the layout shift does not occur, the skeleton screen can be released. But what is the minimum requirement for the layout shift not to occur? This is when each component behind the skeleton screen that covers the entire screen finishes drawing and its height is fixed. In other words, this is when the height of the component entering the screen or viewport is fixed. This is because if a layout shift occurs outside the viewport, the user will not recognize it and will not be a problem. Whether or not the content goes into a viewport is not determined by the API call alone, although it is related to the API. After the API call is completed, the content is drawing and its height is fixed, and only then you can determine whether it is within the screen or not. That means the skeleton screen we implement requires a mechanism to remove the skeleton screen by considering the height of the screen after drawing as well as API calls. So far, I have talked about the problems Line News is facing, the layout shift problem, and the need to introduce skeleton screen as a solution, as well as the need to create our own skeleton screens. The following is a detailed explanation about how we have implemented the skeleton screen in Line News. There are many topics in the implementation of the skeleton screen, so I will discuss it in detail in the following sections. Skeleton screens cannot be implemented as a standalone feature. They must be implemented in accordance with the architecture used by Line News. So I'll give you an overview of the Line News architecture and then introduce the implementation details. The following diagram shows a part of the architecture of Line News. The blue elements on the right of the diagram are React components that make up the News tab and their relationship diagram. In News tab, multiple tabs such as Top and Domestic are placed side by side with corresponding tab components. The component tree containing each tab component receives a state from the store group. When the contents of the store are updated, the tab component is also updated and redrawn. The store stores the data obtained from the action via API. Actions for updating the store can be used in various places. For example, content data required for the first view is stored in the store through actions and APIs when the application is launched. As you may have noticed, this is in accordance with the Flux architecture and is achieved using Flux utils made by Facebook. This is the description of the architecture that makes up the News tab. I will now talk about how we incorporated the skeleton screen into these architectures. First, let's talk about the implementation of the skeleton screen UI component. We aim to make the skeleton screen components wrap and place the tab components. It was actually implemented in two separate components. The first is the skeleton screen component, which is responsible for the design of the skeleton screen. This component does not contain any business logic, but only HTML and CSS styles applied. It is a presentational component in the sense of React. It does not have any state, but only the minimum props required for handling DOM events, such as onTransitionEnd. The second component is the skeleton overlap component, which is used to switch the skeleton screen component described earlier. In addition to switch, we also manage the fade-out animation. This is how it is implemented. It receives the show hide flag from props and passes the value to a custom hook for animation. This custom hook converts from a true-false value for show hide to a state that takes into account the animation state. Based on the state, a class name is given and fade-out animation is applied, and switching the components of the skeleton screen. Now that we can pass props to manage the skeleton screen, so let me now talk about the two heights that are related to the logic that decides show hide. Let's review the conditions for the release of skeleton screen again. The condition to release a skeleton screen that covers the entire screen was when the height of all components drawn in the viewport is fixed. In other words, compare the height of the viewport with the total height of the drawn components behind the skeleton screen, and if the latter is larger, layout shift will not occur and the skeleton screen can disappear. Those two heights will be stored in the store. Whenever the store is updated, the skeleton overlap component will reflect the store state as props, and the skeleton screen can be managed. Store is newly prepared exclusively for skeleton screens. Its structure is defined as skeleton overlap state so that it has two heights required by the skeleton screen's release condition. The first property of state is the height of the viewport.
The height of the screen depends on whether the device is in landscape or portrait mode. So we monitor the orientation change and then use the web API to get it. The second property of state is an array that contains the skeleton overlap tab object that holds the height of the content for each tab. The skeleton overlap tab object provides the height of each component in the tab. It holds the sum of those values. Then compare the sum of the values with the height of the viewport and decide whether to show skeleton screen or not. The value of ready to hide is passed to skeleton overlap component as a props, which enables the skeleton screen to be displayed separately. Now that we have discussed the store that stores the height, I will show you how the height content is determined along with the code. In order for each piece of content to have a definite height, the content must actually be drawn. The data required for drawing is stored in a separate store for each content as a state. Since each content store stores data through the API, the data is stored in the store asynchronously. In other words, the ability to draw a component and determine its height depends on whether the data in the content store is fixed or not. The status of data is called data status and newly added to store of each content. Data status includes, for example, the following states. Indicates that the presence or absence of data is undermined, none, then pending if data is being retrieved via API. When the API acquisition is successful and the existence of data is confirmed, it is called success. As mentioned earlier, if the data status is success, it means that the content will be drawn and the height will be determined. In addition, there are other status besides success in data status. For example, in line news, if data acquisition through the API fails, the content will be hidden. In other words, the height can be set to 0. In this way, the important point is not whether the content data is stored in the store, but whether the data is determined or not. If you are using local storage as a cache, you can also draw the content. In addition, whether or not the content can be rendered is a Boolean value, true or false, so it could be simply managed as a Boolean type, but in order to use the data status in other places in the future and to understand the status more accurately during debugging, it is managed in this way. We will now look at the part that actually stores the data status in the content store. The code shown on the screen is a simplified version of News tab code before the skeleton screen was introduced and before the data status was stored. To call the API, required to draw the content. The result of the API are reflected in the store through the dispatcher. We will modify this action to implement a mechanism to update the data status. The changes we made to bring the status of the data into store is shown in green. The store has an initial value of none, and then changed to pending status before calling API. Pending is represented by the action type. When the API call is successful, it will include the retrieved content data in the payload and dispatch the action type of success. If the API call fails, the store will reflect failed. This is a basic process to determine the height of the content. From here, we will move on to more advanced topics. There is more than one type of data needed to draw content. Some components can only be drawn when multiple pieces of data are available. For example, we need data to display an article, and we also need to categorize it according to the group results of an A/B test. For this reason, we need to consider the conditions for releasing the skeleton screen when relying on multiple stores. If your content depends on more than one store, then check the data status of stores with AND condition. For example, if one of the data is not finalized, such as data B, it can be assumed that the content cannot be drawn yet. When all the dependent data is confirmed, the content is ready to be drawn, and its height is determined. In this way, each component receives its own data, and data status draws it and displays it on the screen. The height can be stored in the store that manages the release of the skeleton screen. At this time, in addition to the height of the component, the index that indicates how many components are placed from the top is also stored. The reason for this is the way the total height is calculated. For example, if you have a layout with 3 components, A, B, and C from the top, you can calculate the total height of the 3 components as follows. Suppose that the height of the A and C components are fixed. If the sum of the heights of the components A and C exceeds the height of the viewpoint, is it safe to remove the skeleton screen? There is a problem with this. If component B is drawn late, it will be pushed down the position of component C, causing a layout shift. In this example, the height to which the component will not be pushed down and the height shouldn't be compared to component A. Let's look at another example. How about when components A and B are displayed and their heights are fixed? In this case, the height is the sum of A and B. In other words, there must be a series of components with fixed heights in order to keep each element from being pushed down. Back to what I said about needing to store the index in addition to the height in the store, when the height of each component is determined, it was necessary to check how far the height of the determined component is contiguous. Finally, we have implemented a utility to improve development efficiently. We have prepared two utilities, useRenderReady and RenderReadyWrapper, to pass the height and index of the component. Both of them have the same function, but they are separated for hooks and for class components. Basically, priority is given to the use of hooks, and when this is not possible, the component utilities are used. Today, we will take an in-depth look at the use of hooks. This hooks is a function which takes the data status of the content and the callback function and return a ref object. These hooks are called from the content component, and the ref object generated inside hooks is tied to the DOM of the content. This allows hooks to retrieve the height of the content. From the data status received as an argument, you can determine whether the height of the content has been determined or not. Then, when the height of the content is fixed, we call the register callback function. In this callback function, we register an action to update the store of the skeleton screen, the table X, which indicates which tab, such as top or domestic. A content index that indicates which component is in the tab. The height of the content is passed as an argument. The above is the implementation of storing the height and an index of a component in the store. These utilities can be applied to existing component implementation or used in new components in the future to reduce the implementation cost of lifting the skeleton screen. So far, we have shown you all the concept and how our skeleton screen was implemented. We tried to do the best we could with the current news tab, but it was not without its problems. Here are some of the problems that plagued us during the implementation of the skeleton screen and what we did about them. The skeleton screen introduced in Line News is a single skeleton screen that covers the entire screen. But in general skeleton screen applies the skeleton screen to each component. So each component can operate the skeleton screen cancellation independently. This means that if a problem occurs where the skeleton screen does not release, we can limit the scope of the problem. It was also clear which component was malfunctioning, which made it easier to identify the cause of the problem. On the other hand, in the skeleton screen method we are introducing this time, the behavior is managed from multiple components behind the scenes, and one skeleton screen is released. If any component fails, the entire skeleton screen will be disabled and the user will not be able to operate the news tab. It also makes it difficult to identify the component that caused the problem. In addition, our unique skeleton screen can be used to clean the skin. If the skeleton screen is not released, it can be fatal to the user when an unexpected problem occurs. When a problem occurs, it is difficult for developers to identify the cause. To address the first problem of users becoming inoperable, we set the timeout for the skeleton screen as a fallback. when the timeout period is reached, the skeleton screen will be released even if the release conditions are not met. The timeout process is only applied to production and some staging environment to make it clear that there is a problem with the skeleton screen release during the development. This way, if there is a problem during the development, the skeleton screen will not be dismissed and you will always know that there is a problem. Next, we added a debugging function for the skeleton screen to be debugging tool for developers, which we have already introduced in the News tab. The debugging tool we call Dev Support runs at the runtime and allows you to check local storage, API call status on a standalone terminal. As a bundled JS that does not affect the service code, we load it only during development. And here is a new debug feature we added to Dev Support called the skeleton screen monitor. There are a few things it can do, but the main ones are: check whether the height of each component has been determined. This will help you to see which component has a release condition. It is a little small, but if you look at the green table, you can see the index and then height of each component, and you can see that the component numbered 0 to 2 in red is a release condition. Since the skeleton screen monitor is available on the actual device used for QA, when a problem is found during QA, we can ask the user to attach a screenshot of a skeleton screen monitor to the bug ticket to reduce the cost of debugging. Lastly, I would like to conclude by talking about the changes that have taken place since the introduction of the skeleton screen and what we can expect in the future. First of all, the problem of layout shift, which was the original purpose of the system, has been solved, and related problems such as use tapping incorrectly have been eliminated. CLS, the Core Web Vitals metrics that measures layout shift, has also improved significantly. CLS requires that the CLS of a page be kept below 0.1 in order to provide excellent user experience, and the original value of 0.348 has been improved to 0.002. The value of 0.002 is also reaction to the intentional rolling animation, which is almost 0. I think it is very good to be able to use this kind of indicator to quantitatively evaluate the effect of the improvements in problems such as layout shift, which may seem difficult to quantify. On the other hand, there is still room for performance improvement in other indicators besides CLS, such as LCP. Especially in the skeleton screen, we have introduced a single skeleton screen that covers the entire screen, so if the loading speed of any content slows down, it will affect the release time of the entire skeleton screen. Therefore, performance tuning is needed to reduce the time to release the skeleton screen in the future. For example, one skeleton screen introduced here can be hybridized with the standard skeleton screen that is released in stages. If the content takes too long to display, it can be removed from the overall skeleton screen removal criteria, and the content can have its own skeleton screen. However, the content that is currently known to be slow online news is advertisements, and the layout size of advertisement changes depending on the result of the API, so we cannot simply make skeleton screen advertisement. In the future, we will try to improve the speed of the first view. This is the end of my presentation. Thank you very much for your attention.